Hello everyone, this is William. Today I want to talk about another dynamic programming problem. The mountain scenes problem is a problem that featured in the 2016 NAIPC programming competition. Although the mountain scenes problem was the easiest problem from that competition, I think there's still a lot we can learn from it, especially for somebody totally new to dynamic programming. Alright, so let's dive into the problem. Let's begin with an abridged problem statement. An artist begins with a roll of red ribbon. She clips it into pieces of various integral lengths, then aligns them at the bottom of a frame, raising vertical columns to form a mountain scene. A mountain scene must be uneven. If all the columns are the same height, then the painting is considered a plane scene, not a mountain scene. It is possible that the artist does not use all of the ribbon. The problem asks, given the length of the ribbon and the width and height of the frame, how many different mountain scenes can she create? Essentially, we're given the dimension of a frame and some amount of units of ribbon, and we want to count all the paintings the artist can make by placing ribbon wherever she likes, as long as those ribbon strips start at the bottom of the frame and raise vertically. In terms of bounds on the input, we are told that n, the amount of ribbon, is bounded between 0 and 10,000. We are also told that the frame's width and height will be no larger than 100. Furthermore, we need to return the number of mountain scenes modulo 10 to the power of 9 plus 7. Below you can see that there are 6 possible mountain scenes when n equals 4, w equals 2, and h equals 2. Remember that the artist does not draw plane scenes, so we should not count the plane scenes illustrated at the bottom of this slide in the final count. Alright, it's time for you to attempt this problem. The best way to get better at dynamic programming is with practice. However, if you start having trouble, I have 2 hints for you. My first hint is that you should try to identify the minimum essential information needed to calculate all mountain scenes. In your DP state, for instance, do you need to track all 3 of n, w, and h? What about only using 2 variables like n and w, or n and h? My second hint is to be sure that you correctly handle the case where you have more ribbon than can possibly fit on the frame. Alright, I hope you have given the problem a try. Now let's look at the solution. The first thing to notice is that you can handle calculating the number of plane scenes and the total number of scenes as 2 different problems. First, I would count all possible paintings, and then I would remove the plane scenes to find the number of mountain scenes. In the example below, we see that there are a total of 9 scenes, but after you remove the flat plane scenes, you are only left with the mountain scenes. Let's begin on the left side of the equation, which requires counting the total number of scenes. One thing I often like to do when solving a dynamic programming problem is to look at what the brute force solution looks like. The recursive implementation of a brute force solution and the optimized dynamic programming solution often share the same transition, which gets you from one state to the next. Here, for example, let's assume the artist is already partially through painting a mountain scene. Suppose she has already laid down 3 units of ribbon up to the second column and that she has 2 more units left to use. What mountain scenes could she draw in the third column? Well, the artist has a few options. She could not place any ribbon in the third column, she could place exactly 1 unit in the third column, or she could place 2 units of ribbon in the third column. Remember that the artist only has a total of 5 units of ribbon, so she wouldn't have enough ribbon to create the displayed mountain scene, so we would not count it. Now that we understand what a transition looks like, let's have a look at a full brute force solution example. In this next example, suppose that we have a frame with a height of 2 and a width of 3, and that our artist has a total of 6 units of ribbon. Let's count how many mountain scenes the artist can create. Starting from an empty canvas, the artist can leave the first column empty, place 1 unit of ribbon in the first column, or place 2 units of ribbon in the first column. After that, she can apply the same logic to placing all the ribbons for the second column by building off all the frames with the first column already processed. Similarly, you can do the same thing for the third column. Every frame which has 2 columns processed gets the third column processed. Instead of having arrows all over the screen, I'm going to represent the expansion with a big arrow. Now, once you have all the scenes generated, don't forget to remove the plain scenes. On this slide, you can see that we have 3 plain scenes: the empty frame, the frame which is half empty, and the full frame. After removing the plain scenes, we are left with a total of 24 mountain scenes. Now let's have a look at the same frame, but when we have fewer units of ribbon. Instead of 6 units of ribbon, suppose our artist only has 4 units of ribbon to work with. In that situation, the same process of tiling applies, except that we are not able to produce some frames. Specifically, we're not able to produce any frames which have 5 or more units of ribbon, so we cannot count them. For all the frames the artist is able to make, this time she can only make 2 plain scenes which have 4 or fewer ribbon units. In total, she is able to produce 23 total scenes, but after removing the plain scenes, that only leaves 21 mountain scenes. From the last example, you may have realized that the branching nature of the brute force method leads to an exponential number of scenes. So even for very small frames where the width and height are greater than 10 or so, this approach wouldn't scale well. Instead, we're going to use a very similar approach to solve this problem inspired by the brute force method. This new method counts the number of scenes based on how many columns the artist has filled so far and how much ribbon she has left. To understand our new approach, let's suppose the artist is partway through tiling the following frames. Assume she has a total of 20 units of ribbon and has already used 11 to create the following 2 different frames. You will notice that both of these frames have used 11 units of ribbon for 2 partially filled mountain scene portraits. Furthermore, remark that both of these scenes have both been tiled up to position 3, but no further. Something very interesting to realize is that the number of ways to tile the remaining section with 9 units of ribbon is the same for both frames. This is true for 2 reasons. First, because we are at the same column index position, and second, because we have the same number of ribbon units left to place. Essentially, you can think of tiling the remaining section as tiling a smaller frame. This is where the dynamic programming optimization comes into play. Let's suppose that you do the hard work of calculating all the ways to tile the remaining section for frame 1. Once you know the number of ways to tile the remaining section for frame 1, you can reuse the same count for frame 2's remaining section and avoid the same calculation. With this approach, the transition from one state to another remains the same. However, before you would attempt to count the number of ways to tile the remaining portion of a frame, you would check if you have already calculated it. Alright, now that we understand the idea behind counting all the scenes, let's take a look at how to count the number of plain scenes, which will allow us to find the number of mountain scenes. Let's begin by manually counting the number of plain scenes for a fixed frame size with different amounts of ribbon. For a frame with a width of 3 and a height of 4, when we have 1 unit of ribbon, the only possible plain scene we can make is the empty scene. We cannot make any more planes because we only have 1 unit of ribbon and we need at least 3 units of ribbon to tile the next plane. However, when we have 5 units of ribbon, we can make 2 plane scenes, the empty plane and the plane with 1 level of tiles. When we have 9 units of ribbon, we can make 4 planes. And when we have 100 units of ribbon, we can make 5 plane scenes. Notice that having more ribbon than can be placed on the frame won't help you make more plane scenes. From the previous examples, it seems like the number of planes is determined by how many full rows can be created based on how much ribbon we have while not exceeding the frame capacity. Therefore, to count the number of plane scenes, I first normalize the number of ribbon squares to make sure that we don't have more ribbon squares than can be placed on the frame. Then I count the number of planes by counting the number of full rows that can be made. I also add +1 to account for the empty scene, which is always a plane scene we need to exclude. As an example, suppose we have a frame with a width of 3 and a height of 4 and 100 units of ribbon, then we would get a total of 12 ribbon squares and 5 planes. Awesome. Now that we know all the pieces of the puzzle, let's have a look at some pseudocode. To begin with, assume that n, the amount of ribbon, w, the width of the frame, and h, the height of the frame, are all accessible globally as constants. First, we have the mod value, which is 1,000,000,007. After that, I initialize a 2D integer table with w plus 1 rows and n plus 1 columns. Assume that all cells are originally null so that we can easily identify the absence of a value. Now we're inside the solve method, which calculates the number of mountain scenes. The first thing we do is find the number of planes based on the dimension of the frame and how much ribbon we have. After that, I call the function f, which is responsible for counting the total number of scenes. For that, we only need to keep track of 2 values: the current column index, which you can also think of as the width up to which we have tiled the frame. Second, I also keep track of how much ribbon we have left, since this will impact how many unique scenes the artist is able to make. When f is called in the solve method, I originally pass in 1 as the starting column index, and provide n as the amount of ribbon our artist has to work with. As a side note, you could also pass in the ribbon squares variable as the amount of ribbon the artist has to work with instead of n. The worst case is the same, so you don't gain much by using ribbon squares instead of n. Inside f, if we ever have a negative amount of ribbon, then we don't have enough ribbon material to tile the frame, so return a count of 0. However, when the width value exceeds the frame width, then we know we have finished tiling a frame. In this case, return a count of 1. The difference between the brute force approach and the dynamic programming solution lies solely in this one line. Without this one line, we are essentially doing the brute force approach. This line simply checks the memo table to see if we have already calculated the number of ways to tile the frame with the current width and ribbon amount. Next, we are trying all possible ribbon lengths for this column. Notice that the length for the amount of ribbon we are trying to place starts at 0 and goes up to the height of the frame. The length starts at 0 because we want to include the possibility of not placing any ribbons in this column. Then inside the loop, recursively call f for a smaller subproblem, and subtract the amount of ribbon we placed in the current column from the total amount of ribbon the artist has left to place. Make sure to add and mod the whole thing. Then the last line does 2 things. First, it stores the result in the DP table and then returns the value. After we get an answer for the total number of scenes, remove the number of plane scenes and apply the mod. Even though the answer returned from the recursive function is mod 10 to the power of 9 plus 7, subtracting the number of planes could make the answer negative, which we want to avoid. So to avoid that, I add the mod and mod again. This ensures that the result is always between 0 and 10 to the 9 plus 7, non-inclusive. While talking about modding values, there's a neat optimization you can do to increase the runtime speed by a little over a factor of 2. Instead of incrementally applying the mod operator inside the loop, only apply the mod outside the loop. Excessive modding can become an expensive operation if done too many times. This is why you usually prefer to mod only at the very end. However, make sure you're using 64-bit numbers if you're going to do this optimization. Otherwise, you will run into overflow issues with 32-bit numbers. Alright, and that's all for this problem. I hope you learned something, and I will see you next time. Please give this video a like if you learned something, and subscribe for more mathematics and computer science videos.